It's a pleasure to have Adam Bouland in our Zoom meetings. Adam is a local, so from UC Berkeley, and he's going to talk to us about pseudorandomness and the AdS CFT correspondence. So please, Adam.
Great. Yeah. Thanks so much for having me. So yeah, so as Hugo was saying, so I'll be telling you about pseudorandomness and the AdS CFT correspondence. Of course, this is kind of the physics title of my talk. Of course, in the spirit of AdS CFT, there should also be a computer science dual to this title. So the computer science dual of the title would be block ciphers and their applications to quantum gravity. And this is based on joint work with Bill Fefferman and Vazirani. Okay, so the starting point to this talk is an interesting question, which is, could quantum circuit complexity be physical? That is, could quantum circuit complexity be a measurable quantity like heat or light or sound or distance or time, like some quantity that you can measure? And at first glance, this might sound like a somewhat strange philosophical question, but it's actually been very seriously proposed that circuit complexity might play a substantial role in the context of black holes, and in particular in the AdS CFT correspondence. So this is an idea that kind of emerged out of from qubit collaboration. In particular, was a proposal of Susskind and many collaborators. And this proposal is really talking about circuit complexity's role in something called the AdS CFT correspondence. So I'm sure many of you are familiar with this, but kind of my cartoon picture of the AdS CFT correspondence is it's this conjecture duality between a quantum gravity theory in anti-de Sitter space, some theory that lives on the left, and a quantum mechanical theory, namely a conformal field theory that lives on the right. And what do I mean when I say it's a conjecture duality? Well, I mean that there is some dictionary map called the AdS CFT dictionary that maps states in one theory to states in the other theory, and operators in one theory to operators in the other theory. And this dictionary is supposed to be, in some sense, a homomorphism between the theories, so that kind of, like time evolution and various things you could do on one theory all have kind of a corresponding behavior in the other theory and vice versa. So you can see why this is kind of really of interest to quantum gravity theorists, because you can kind of see this in some sort of naive way as a recipe for constructing a theory of quantum gravity on the left-hand side. This theory that physicists have been searching for since Einstein and Hawking in the 1930s. You can do this by studying its dual quantum mechanical theory on the right-hand side. And the hope is that by studying this correspondence, one might be able to learn new things about quantum gravity. And this is something that's been kind of a very fruitful way of understanding quantum gravity. I would say that this dictionary is something that hasn't been fully worked out, so I'd say it's something that's under construction. But I think that physicists have very good reason to believe that this dictionary exists and have already learned new things about quantum gravity and the nature of space-time, such as things about error-correcting codes and things like this, that would maybe not have been easy to see without this AdS CFT correspondence. Now, one challenge to understanding the AdS CFT correspondence is something called the wormhole growth paradox, which was first identified by Susskind in 2014. And the paradox is really simple to state. So the paradox begins by noting that there's some certain mismatch in equilibrium properties of gravity theories versus their dual quantum mechanical theories. So what do I mean by this? Well, in particular, in quantum gravity in an AdS in anti-de Sitter space, we know that there are certain solutions to Einstein's equations called two-sided wormholes. And these are systems that in classical GR, they do not equilibrate really ever. So in classical GR, this wormhole the geometry of this wormhole just kind of stretches linearly, and it keeps growing that way for an infinite amount of time. So we know that in a quantum mechanical form of a gravity theory, there's probably some finite dimensional Hilbert space. So, you shouldn't be able to actually grow the wormhole forever. There should be some recurrence. But I think it's safe to say that this wormhole is something that should not equilibrate for at least an exponential amount of time. Exponential here in the mass of the black hole, or say the entropy of the black hole. So if you were to plot, say, the wormhole volume versus time, the graph would look something like this. It's just something that grows linearly, basically forever. Now, this stands in sharp contrast to the properties are believed to hold for the quantum mechanical theory. So the quantum mechanical duals to black holes are believed to be rapidly scrambling. So there are theories that kind of, like, maybe naively, the way to think of it is that they kind of look like a blender. Whatever quantum state you put in it, the quantum state kind of rapidly thermalizes and kind of comes to equilibrium. So what do I mean by that a little more concretely? Well, let's say that you picked a local operator O in your conformal field theory on the right-hand side, and you wanted to plot, say, the expectation value of O with this state over time. What you would see is that this quantity would equilibrate very rapidly. In particular, it would equilibrate in polynomial time. So this gives rise to a natural question. If there's this duality between these two theories, what quantity in this right-hand theory could possibly be the dual to wormhole volume? From the things I've just told you, we already know it can't be some locally defined property of the quantum mechanical theory. So it has to be some kind of weird and non-locally defined quantity. But what could that quantity possibly be in the theory that scrambles? So this was the paradox that was first put forward by Susskind. And in the same paper in which he noted this paradox, he also proposed a resolution of this paradox. And his resolution was that circuit complexity is physical. That is, he conjectured that the quantum mechanical dual to wormhole volume is the quantum circuit complexity of the dual state. So this is sometimes called the complexity equals volume conjecture, because it's saying the complexity of the CFT state is the dual to the volume of the AdS state. There's a bunch of kind of closely related conjectures, such as complexity equals action conjecture. Our arguments wound up applying to those conjectures as well. But this was the basic proposal of Susskind. So what was the intuition behind this proposed resolution of the paradox? Well, the intuition goes something like this. So let's say that you have some initial state psi of your conformal field theory, and you time evolve it by the CFT Hamiltonian H. So you have some states, which is like e to the minus IHT times psi. And that state, you can think of it as just applying some kind of fixed unitary u over and over again to this initial state psi. If you were to say discretize time into, say, unit chunks, this would, if u is evolution for 1 unit time, then the state at time t would be u to the t times psi. And the basic idea is that the complexity of the state e to the IHT times psi relative to psi, that is to say, what's the size of the minimum quantum circuit you need to transform psi into e to the IHT psi. The intuition is that this circuit complexity is something that should grow linearly, because there shouldn't be any shortcuts to preparing the states, right? So, one particular way of generating e to the IHT psi from psi is just to apply this Hamiltonian evolution, say by some quantum Hamiltonian simulation algorithm. And that would take time, which would scale, roughly t, or at least polynomial in t. And the intuition is that maybe for these particular unitaries u that are being considered, that these very scrambling CFT evolutions, that maybe that algorithm is basically the optimal one. So kind of intuitively, in this picture, you would expect that the complexity, say for typical Hamiltonians H, that the complexity is something that would grow linearly with time. Now, even this statement itself is not something that's obvious. And as a result, there's been a lot of works trying to create supporting evidence for this conjecture. So one kind of family of works by Aronson and Brandau and Bodanowicz and Balasubramanian et al. Have kind of shown that from the complexity side, they've shown that there are certain kind of necessary but not sufficient conditions that this Hamiltonian H could satisfy, which would make it plausible that the complexity, of these states would actually grow linearly with time. So these are works where, they're trying to support this conjecture, but from the CFT side, from the right-hand side quantum theory. On the other hand, there have been other works which have kind of been starting more from the gravity side, works of Stanford and Susskind, Stanford and Schenker, and many others, which have tried to justify kind of why, from the gravity side, why volume should behave in the same way as complexity. So in particular, what these works did is they said, well, let's consider some small perturbations to this evolution, and kind of, say some local operator insertions. That this is something that I'll discuss in more detail shortly. But they kind of took certain perturbations to this evolution, and they showed that, what would happen on the gravity side, how the behavior of the volume would change due to these perturbations exactly matched, at least up to leading order, how you would expect the complexity of the states to change. So
okay,
this
so
is,
sorry,
go ahead.
You have a question in the chat.
Yeah, sure. Yeah, if you can go ahead and read it to me, that would be great.
Yeah, someone said, could you define circuit complexity here? Are you talking about the number of two local gates specifically?
Yes, exactly. So by circuit complexity, I think, the most natural definition would be say, what's the minimum number of two local gates you need to apply to produce the state e to the IHT psi, starting from the initial state psi. And you say up to some amount of error epsilon. Now, it's not entirely clear that this definition is, say, gate set independent or something like this. So there's some kind of subtleties here that need to be worked out. And there have been actually several works trying to define, in the CFT, what's actually the correct definition of circuit complexity. But we'll just be thinking about qubits in this talk. So let's take, say, minimum number of 2 qubit gates to approximately prepare it as our canonical definition. Great. All right, so so that's kind of the, that was kind of the status of this conjecture and the evidence kind of supporting it. But now when we look at this, when one looks at this proposed resolution of this paradox from a computer science perspective, it usually strikes computer scientists as a very strange proposal. In particular, computer scientists would say, well, like, you're saying circuit complexity is physical, here be dragons, like, so something should be very wrong here. So why is that? Why do computer scientists have such a strong reaction to this conjecture? Well, it's that there seems to be some sort of tight mismatch between complexity and wormhole volume that makes computer scientists very uncomfortable. The basic reason is that circuit complexity is something that we know in computer science is something that should be very difficult to feel or estimate. Actually, this observation that circuit complexity is something that's very difficult to compute, this is an observation which goes back to, say, the late 80s, early 90s. It actually emerged from as a way of understanding certain obstacles to separating P versus NP. But this is something that's kind of very well known in theoretical computer science. And I'll discuss this a little more in the context of AdS CFT shortly. Okay, so the second reason that one might have discomfort with this conjecture is that the wormhole volume sounds like something that should be easy to estimate or feel. Yeah, sure. Go ahead.
I just wanted to make sure I understood. So for the first statement, do you mean this as an average case statement or as a worst case statement?
Sure. So even as an average case statement, complexity is something that can be difficult to feel or estimate. And the intuitions for this actually come from cryptography. And I'll actually explain that a little more in detail later in the talk, exactly what part of complexity theory is kind of telling us that complexity should be difficult, and kind of how we can instantiate this in the context of AdS CFT. But it will be an average case statement. As in, like, even typical states it's difficult to feel their complexity. Great. Okay, so this seems like a bit of a tight mismatch. So this is now saying that this conjecture is connecting something that's difficult to estimate with some quantity that's easy to estimate. That seems kind of wrong. Okay, but this discomfort actually turns out to be very challenging to formalize. And that's for two reasons. So the first reason is that in the context of complexity equals volume, only a very special subset of states are even being considered in this conjecture. It's not, say, any state you could prepare with 2-qubit circuits of some certain size. They're really talking about some very specific ensembles of quantum states. And one might wonder, like maybe the circuit complexity of these states is something that's actually easier to estimate than it is for general states, which were dreamed up by computer scientists. The second reason it's not obvious that this mismatch is instantiated in AdS-CFT is that if you look at classical GR, it turns out that in these two-sided AdS wormholes, that no single observer in the black hole can actually estimate the volume. The reason is that any person who jumps inside the black hole actually dies in some finite amount of time, kind of regardless of the length of the wormhole. So they actually don't have enough time before they die to take out a ruler and kind of measure the length of the wormhole. It's something that's not in their. It's something that's not accessible to them. So maybe this wormhole volume then is something that's just not accessible in this theory at all. So that would also kind of get one out of this type mismatch conundrum.
So Adam,
yeah, sure.
so I have a question. So do you think this thing is a specific problem for a specific kind of connection for gravity, or you think it is more general? For instance, let's consider the fluid dynamics. Let's say I have a bunch of atoms, and then I want to compute some complicated object. It seems to be computationally hard. And then I write down a collective field theory, and then I see an emergence of fluid dynamics. And then I try to track the fluid dynamics, which looks computationally easy. So do you think this is similar with AdS-CFT, or it is completely different?
Well, I think some issues like this could arise in any duality where you're kind of trying to map something hard to compute to something that's easy to compute, right? So I think, yeah, this is something that one should be aware of whenever you're trying to do this. Of course, if you actually map something hard to compute to something easy to compute, and that transformation is very simple, and then that would be actually kind of a proof that the thing you thought was hard to compute on one side wasn't hard to compute after all, right? So I think the interpretation of these sorts of statements would be very context specific. But today I'm really only going to be talking about this in the AdS-CFT duality context, and only in the two-sided black hole context. And I'll raise the question about with one-sided black holes later on in the kind of open question section.
Okay, thank you.
Yeah, great. Yeah, thanks for a great question. So, okay, so in this work, what we sought out to do is we tried to ask, can these objections that computer scientists make, can these be realized in this model of two-sided AdS wormholes? And if so, what would this mean for the AdS-CFT correspondence?
Adam, can I ask a question as well?
Yeah, sure.
Just about the rules of the game. So, for example, if you handed me the quantum state at some late time, I mean, I don't know this, but you got this quantum state by running the CFT Hamiltonian for a really long time.
Sure.
And I'm supposed to figure out how complex it is. Are the rules of the game that I know that you got it by running the CFT Hamiltonian, so I can just simply run it backwards and wait how long it takes for it to become simple? Or are the rules of the game that you could have gotten it using any set of unitary operators that come from simple gates?
So good question. So in our work, we're going to be assuming that you know the Hamiltonian of the CFT and you can apply it forwards or backwards as you like. But we're actually never going to be talking about states at late times. We're only talking about early times, say polynomial in the mass of the black hole, say. So so as a result, there's not really any there's not really any case in which it would make sense to run, that Hamiltonian evolution for an exponential amount of time. So everything's going to be polynomial time bounded.
I see, but the key thing is that you're going to throw in some other ingredients that's going to make it difficult for
Exactly. We're going to throw in some other ingredients that are going to make it more difficult to feel the complexity. Exactly.
That is that almost meaning that Hamiltonian you don't know? It's external.
Well,
force.
it would say that there's some aspects of the evolution that you didn't
Yeah.
know. But yeah. But I'll get to this in a little more detail when I describe the explicit model. Great. Okay. Great. So so that's kind of one's intuitive discomfort. And at a very high level, our result is to instantiate this discomfort in the context of AdS CFT. So in particular, our first result is that we created the form of something called computational pseudorandomness within the dual quantum theory. And what computational pseudorandomness is at a very high level is it's an ensemble of quantum states which are very difficult to distinguish from one another, but which have very different complexities and hence very different wormhole volumes from one another. So what this means is that it will mean that whatever the dual to volume is, it would be something that would be very difficult to compute in the CFT. So once you create computational pseudorandomness, it immediately implies complexity is hard to feel, but it also implies any quantity that grows linearly with time is something that would be very difficult to estimate as well.
Can I ask briefly a
Yeah,
physics way of interpreting
Mm-hmm.
what you mean by an ensemble of quantum states which are difficult to distinguish from each other, but with different wormhole volumes?
Yes.
Like, can I think of, is one way of saying this that ETH applies to this ensemble of quantum states?
I'm not sure if, yeah, that I don't know if that's the right way to view it.
Well,
I think really the right way to
with
view
what?
it is kind of cryptographically, that there is some like secret information or some secret key you don't have about these states. And by not seeing that secret key that's controlling some parameters or some perturbations to the evolution, it then makes it really hard to tell a random one of these states from one another. But I'll get to the formal definition of this in a few slides.
Well, so the reason why I'm asking this is because
Mhm.
the reason why I'm asking this is because if things are difficult to distinguish from each other in the ETH sense,
Sure.
then one of the consequences is that any low point observable that you construct for any of these states is going to be the same or roughly indistinguishable. If I look at
That's right. That would be a
different states.
consequence of this. If you have a computational pseudo-random state ensemble, then it would mean by definition that some simple local observables would not distinguish them.
But nevertheless, it's possible to do that while having differing wormhole volumes, is your point.
Yes, exactly. And that's what I'll describe in a little more detail in a few slides. So,
Okay.
great. Okay, so that's the first part of our argument.
Also, a very quick question about this. So when you mean that they have different wormhole volumes, do you mean that they're different like polynomially, or they're different
I'm
exponentially?
going to mean polynomially.
Okay.
And I'm going to mean, like say one is, if n is the entry of the black hole, one's length n squared and the other is length n cubed. And here I'm using wormhole volume and length of time evolution you use to get the state kind of interchangeably, because whatever the dual to wormhole volume is, it has to be something that grows kind of roughly linearly with your time evolution. So, yeah, great. Okay, so that's
sorry,
yeah, go ahead.
I have another question. So at this step, can you be sure that this computational pseudo-random state in the dual CFT has a well-defined gravitational interpretation? Can you say that?
So that's something that we're going to have to be very careful about. And when I describe the ensemble, you'll see exactly how we designed it to ensure that it has a well-defined gravity dual. Yeah, that's a great question.
Okay, thank you.
Yeah, thanks. Okay, so that's kind of the very high level sketch of this first statement. The second statement is that we showed that the wormhole volume is easy to compute given the AdS state. And actually, this second point is a little more subtle, because you might ask, how is that consistent with what I just said, that no one observer can measure the wormhole volume? But our argument will be saying something slightly differently, what we're going to say is something like, if you could somehow combine the experiences of many space-like separated observers within the wormhole, then from this, one would be able to extract some coarse estimate of the wormhole volume in polynomial time. And that statement actually turns out to be enough to create some tension with this pseudorandomness property that's indicated in the first point.
So I don't understand that statement, because it's equivalent to saying that the first one is wrong. I mean, I don't understand why you care about observers in the first place if you're then going to let several that can never talk to each other. Because in that case, we could have called that one observer.
Sure. So it's not an immediate contradiction to one. If you show two, it doesn't immediately contradict one. So I'll describe what this actually implies kind of in the next slide. But I think the point of the second point is that even if physically one could never measure the volume if one lived in the space, if one lived in the AdS, there could be some sense in which it's computationally, the information is computationally accessible from the quantum gravity state, even if it's not physically accessible.
There's something that you're not saying, and I'm trying to understand why you're not saying it. So let me say it, and then you can tell me why you don't say it.
Okay, sure. It could also be because it's on the next slide.
That's possible, and I'm so sorry if that's what's going to happen. But
that's okay.
But you could have just said, well, it would already be a contradiction with one if it was somehow easy to construct the gravity state from the given quantum state, and then use classical gravity, just figure out how simple, how long you had to run it.
Exactly. That's exactly what I'm about to say. So what does this mean? This is kind of exactly what Raphael was saying. So what kind of this means for AdS CFT is it means kind of whatever this dual quantity to wormhole volume is on the right-hand side, it has to be something difficult to compute, like complexity. This is a consequence of pseudorandomness. Then on the other hand, whatever, this wormhole volume is something that's easy to compute. It's extractable with some small number of copies of the AdS state in polynomial time. So what does this mean for AdS CFT? Well, this means that this duality has to be connecting some quantity that's difficult to compute and turning it into a quantity that's easy to compute. In particular, what would that imply? That would imply that this dictionary has to be something that is itself exponentially difficult to compute. Because otherwise, there would be a contradiction, right? Otherwise, you could take your CFT state, apply the dictionary efficiently compute the volume, then that would allow you to break the pseudorandomness construction on the right-hand side, which contradicts the pseudorandomness property. So that's kind of exactly what this implies for quantum gravity. Though so you can see this as saying that this AdS CFT dictionary is something that needs to be permanently under construction. So in other words, while we might be able to learn a huge amount about quantum gravity from AdS CFT, it might be that certain aspects of the AdS CFT dictionary, such as reconstructing wormhole interiors, is something that is actually exponentially prohibitive to perform even with a quantum computer. And this could actually explain in some ways, why it's so difficult to understand, say, quantum gravity in wormhole interiors.
Just to make sure.
Sure.
But only if you assume that there is you don't have a complete knowledge about the complete system, right? Because if you know everything, then you just a Hamiltonian, and if you have a perfect knowledge about the state and then evolve backwards,
there's going to be some sort of hidden knowledge in our construction. Though that hidden knowledge, I would argue, can be just seen as a thought experiment rather than something one would have to actually perform in the theory. So I'll explain that a little more once I describe the exact model.
So Adam, one thing that I think might be helpful for the people that are more high energy in the audience is for you to just say a few words, if possible, about the fact that the pseudo-randomness conjecture is extraordinarily well motivated. So it's unlikely that that's the thing that's wrong. And
so as I'll explain shortly, this pseudo-randomness conjecture, the construction that we use to create this kind of pseudo-randomness statement in the CFT is actually inspired by classical cryptographic constructions called block ciphers, such as the AES and DES crypto systems. So they're on pretty firm kind of computer science grounds. And I'll explain that in a little more detail exactly how this pseudorandomness construction is actually connected to block ciphers. Yeah, so that kind of makes one think that if the thing that might have to give here might have to be the exponential complexity of the dictionary. I do also want to mention that there's one other out from this argument, which is that another way of kind of getting out of this contradiction is it could be that something called the quantum extended Church-Turing thesis is false in quantum gravity. Okay, so for those of you who aren't familiar with it, the quantum extended Church-Turing thesis is the conjecture that all physical phenomena are efficiently simulable on quantum computers. And thus far, this has been true of all physical theories that we know of. There have even been work showing that certain quantities in quantum field theory are actually efficiently computable on quantum computers. And in order to make our argument work, we have to assume this quantum extended Church-Turing thesis holds in the wormhole interior in order to simulate the experience of these observers living in the gravity theory efficiently. So one other possibility of our result is that it could actually be that the dictionary is simple to compute, but just that it's exponentially difficult to simulate what happens to observers living in the interiors of wormholes in quantum gravity.
Can I ask you, I don't doubt the pseudorandomness thing and the quantum extended Church-Turing thesis being on solid ground. The thing that I'm struggling with is why it's supposed to be such a big deal that the dictionary is exponentially difficult to compute. You said something about that, which I didn't successfully process, I think, because to me that would seem like the obvious way out, and I don't really have any problem with that. But I think I should be having a problem with it.
Yeah. So I'll talk a little bit more about interpretations of this on my last slide of the talk. But if you're okay with an exponentially complex dictionary, then this is kind of reasonable. I think it's something that maybe from a computer science perspective, it's something that maybe computer scientists found surprising. And the basic reason is that when computer scientists think about dualities like this, like linear programming or semi-definite programming dualities, usually this mapping between the dual theories is something that's efficiently computable. And this is kind of a major algorithmic paradigm in theoretical computer science, is to use the fact that you can switch between kind of linear program or semi-definite program duals and primals efficiently. That's kind of a cornerstone of theoretical computer science. And this is kind of very concretely pointing to why that's not the case in this theory.
Well,
and,
I think there's a key thing that maybe I want to stress a little bit that hasn't been mentioned, which is that I think most physicists that I know at least would say that this is not a duality in the sense of an equivalence.
Yeah.
That on the gravity side, we have an approximate theory, and the CFT is its non-perturbative completion.
Sure.
And it's actually the only complete theory that we can use. So from that viewpoint, I don't think this is on the same footing as the kind of examples that you've just mentioned. And I wouldn't find it surprising at all that there are states that I've evolved for a long time using this quantum mechanical theory, where it becomes difficult to figure out whether or not there exists a simple description in terms of this more approximate theory of those same states.
The thing is that our construction will entirely be of states which are low energy states of the CFT and which have only evolved for a polynomial amount of time. So actually I would say that one of the kind of main obstacles we had to solve in order to make this argument was to try to figure out how to cram pseudo-randomness into this kind of small corner of states in the CFT, which have these reasonable gravity duals. So I would actually say that this implies that this dictionary is hard to compute, kind of even in that small subset of theory. Like it's not something that only occurs, say, if you evolve to super late times and you get the kind of typical state.
But I thought the challenge is to distinguish this kind of state, for example, from one that you didn't generate, which might have taken a much longer time. That's hard.
No, it's actually, we'll actually be arguing about we're going to argue it's hard to distinguish two states that evolved for different times that were each polynomial amounts of time. So they're still relatively early times. If that makes any sense. So we never actually even discuss evolution for exponential time in the paper. So.
So Adam, about this quantum extended charge turning thesis, because I'm not completely from a computer science background, and more part of me are high energy. So I want to ask you that. So I take a look on the history of charge turning thesis. So there are two. So one type of charge turning thesis is not related to the efficiency anymore.
Yes,
so it is just says that you could simulate or you could not simulate, so that is a core problem. Even if it is exponentially hard, then it's fine. You can wait for exponentially amount of time, then you're okay. But another type of the theory of this thesis is based on complexity, which says that you have to efficiently simulate, which means that you, So why people believe,
that's the extended church Turing thesis is the statement that you should be able to simulate the other system with only polynomial overhead. I think the perspective is that kind of the church Turing thesis is, or even the extended church Turing thesis is something that has held kind of essentially since it was founded, since it was dreamed up by Church and Turing, way back in the early 20th century. And it wasn't until quantum computation was invented in the 90s that we realized that, at least on a theoretical level, that this should be false, that there should be some things that you can efficiently compute with quantum computers that it's not clear you can efficiently compute with classical computers. So then there was kind of this modification made called this quantum extended church Turing thesis, which is that, well, okay, if you had a quantum computer, then you could simulate all physical processes. And so far, this is held for all physical theories that we've been able to come up with so far. But yeah, I think it's now whether or not this is true is something that's at the borderline between physics and computer science and philosophy, of course. I think computer scientists tend to be fairly fond of the quantum extended church Turing thesis. I certainly am, and I'd say there's been evidence supporting it. But it certainly, I'd be open to the possibility that it could be false in some kind of exotic physical system like the interior of a wormhole. But I think most computer scientists would still find it surprising if it failed there.
So why people sometimes use extended, the word extended? It means that the quantum is still classical?
So extended here means with only polynomial overhead. So in other words, you can simulate the other theory efficiently. So yeah.
I see. So extended here means efficiency.
Yes, exactly.
Okay. Yeah. Yep. Another question about this. Yeah, it's about the definition of time. So you're saying that exponentially hard, which means that you have, but you didn't define time in general relativity. If I perform a redshift I
agree. There are great questions to formalizing exactly what one means by quantum extended church Turing thesis. Clearly, you would need to take care of some issues like this, like redshifting, to kind of be able to do a computation more efficiently. Of course, redshifting would cost a huge amount of energy. So maybe there's some time energy equivalence. Maybe you have to say the amount of time plus the amount of energy you need is that. But I'd actually kind of prefer to shelve this discussion for the moment so that I can get to the result. But I think they're interesting questions.
Is that just a boundary thermal time? Unit is boundary thermal time.
No, here. The quantum extended church Turing thesis, we're applying it to the AdS side. So we're actually applying it we're saying that the experiences of the observers living in the wormhole is efficiently simulable. So, those observers are living in the relativistic theory. So there would be some issues like that could crop up. Great. So anyways, I'm going to move on, if you don't mind, to the kind of basics of the construction. But I'm happy to take more questions about interpretation later, because I have one slide at the end of the talk kind of giving some different ways of interpreting this result. Great. So I'm now going to briefly explain the core argument that we had, which is why are the states in the CFT computationally pseudorandom? Okay, so in order to answer this question, we first need to understand kind of what states are allowed in the CFT in the first place. So in order to do this, we're going to make a qubit toy model of the CFT. So we're going to model the CFT with a system of n qubits, where n is the entropy of the black hole. This is for concreteness. Now, the initial state, say at time 0 of the wormhole, is something called the thermal field double state, or the TFD state. And the details of what the thermal field double state are actually won't matter much for this talk. All you need to know is that it's a relatively low energy state of the CFT Hamiltonian HCFT. Now, the states of the CFT then evolves according to this CFT Hamiltonian, but e to the minus IHT. And it's going to be helpful to think of a discretized form of this evolution. So we know that within this conformal field theory, there's some characteristic time called the scrambling time. And this is the time at which this Hamiltonian evolution kind of diffuses local perturbations throughout the system. So let's denote evolution by a scrambling time by this unitary U. And the most basic allowed states in the CFT are the states where you just apply this unitary U over and over again to the initial thermal field double state. But now it turns out that if those were the only states we were talking about, then this theory wouldn't be kind of very rich. It would be kind of a very simple theory. But it turns out that it's actually reasonable to talk about a slightly broader class of states in the conformal field theory, namely those states that you obtain by this time evolution, and then slightly perturbing them by inserting some small number L of, say, single qubit gates into the evolution.
Adam?
Yeah, sure.
So you talked about a thermal field double. Does that mean that you are modeling a two-sided black hole and you have two quantum systems that evolve independently of each other?
Yes, that's correct, though the details of that won't actually matter for this. You can just make our entire argument living in one side of the CFT, and that's the side in which everything is scrambling, et cetera. Yeah, but that's a great question. Okay, so why are you allowed to kind of make these perturbations? Well, the basic idea is that these single qubit gate operations, you should think of them as analogous to applying some, say, thermal scale operator, some low energy operator to the conformal field theory. Now, each one of those operator insertions will slightly increase the energy of your state in the CFT by a small amount, right? Because in general, if you have some Hamiltonian, you have some relatively low energy state, then you perturb it locally, then it will increase the energy density of that state locally by some amount. So it will actually add some energy to the system. And on the gravity side, these small perturbations corresponding to applying shock waves to the AdS states, which throw some energy into the wormhole. And this actually perturbs the wormhole geometry in some simple way. So the state that you obtain in the CFT then, after the insertion of L's shocks, looks something like this. Like, say you evolve by U, then you apply some operator O1, which is a 1 qubit gate, then you evolve by U, apply another operator, et cetera, et cetera. So you should think of these states as they're basically like the normal time evolution of the thermal field double state, but with some small perturbations to it, with some small local operators inserted along the way. And one of the main bits of evidence in support of complexity equals volume was actually these works by Stanford and Schenker and Stanford and Susskind, which showed that the changes to the wormhole's volume that are induced by throwing in shocks actually roughly matches the changes in the complexity of these states that occur on the right-hand side under adding these 1 qubit operator insertions. So these are precisely the states that were kind of being talked about in the literature before as part of the evidence for complex equals volume. So these are the states we're going to be talking about in this talk. And note that here we're limiting the number of insertions applied to be very small, and that's in order to ensure that we remain in a relatively low energy state of the CFT. So a central question is then, how hard is it to estimate the complexity of states of this above form? Well, let's formalize that a little bit more. So more formally, we'd say, let's suppose you were given many copies of a state of the above form, you might ask, how difficult is it to estimate the circuit complexity of that state, which is roughly proportional to the number of times you applied U. Now, the standard tool that one often uses in this area to try to argue that it's hard to estimate the complexity of the states would be to show that these states, this ensemble of states over some, say, suitable choice of random operator insertions form a unitary T design. In other words, you might hope that maybe you could show that some ensemble of these states matches the first T moments of the Haar measure. And that would then mean that these states would be information theoretically indistinguishable from Haar random states. And that would immediately imply that it's hard to estimate the complexity of these states, because we know that Haar random states have maximal complexity. These states by construction have only small complexity, polynomial complexity. So if these states are indistinguishable from random, it immediately implies it's difficult to estimate their complexity. Okay, so that's really great. And these T designs have been really useful for understanding quantum gravity in general. But unfortunately, this technique is not something that will work to answer our problem. The reason is that actually there's a simple counting argument that shows you that any ensemble of states of this form, if you only applied much fewer than n operator insertions, couldn't possibly form even a unitary 1 design, just by the fact that you need at least 4 to the n distinct states to form a unitary 1 design, but we only have 4 to the L states where L is much less than n. Okay, so this means that these states are information theoretically distinguishable from random. So in this work, we're going to have to use an alternative tool, which is we're going to try to argue that these states are computationally pseudorandom. That is, even though they are information theoretically distinguishable from random, kind of that information is not something that's efficiently accessible to polynomial time computation. And this is an idea that is really central to cryptography. And so in fact, this idea was recently kind of ported over to the quantum setting by recent works of Ji, Liu, and Song. So let me be a little bit more formal by what I mean by computational pseudorandomness. So let's say that you have some collection of states psi k. This is some ensemble of states on n qubits, which are indexed by some string k of length m. So this is some collection of, say, 2 to the m different quantum states. So we'll call this collection of states a quantum pseudorandom state ensemble, or PRS, if it obeys 2 properties. The first is that it's possible to efficiently prepare these states. So that's to say, each one of these states psi k, you can create in polynomial time from some initial reference state. But on the other hand, we want them to obey a second property, which is called computational indistinguishability. So we want it to be that, if I gave you any number of copies of this state, any polynomial number of copies of this state, then these states are not BQP distinguishable from the same number of copies of a Haar random state. So let me unpack that a little bit. So what I'm saying is that, let's say I picked a random psi k, and I gave you a whole bunch of copies. Then that would be, then there's no polytime quantum computation that you could perform to distinguish that from if I had handed you, that many copies of a fixed Haar random state. Okay, so this the definition of a pseudo-random state ensemble makes sense to everyone? Okay, so I'll move on. And one nice thing that that was pointed out by Ji, Liu, and Song, and also follow-up works of Berkersky and Shmueli, is that there actually are efficient constructions of quantum pseudo-random state ensembles. In particular, these constructions use something called a pseudo-random function. In particular, they showed something like if you have some function, which is a pseudo-random function, f sub k, indexed by some secret key state, then if you created a state by taking an equal superposition over strings and applying pseudo-random phases to them, then these states would be provably computationally indistinguishable from the same number of copies of a Haar random state. So the details of this is really not important. The only takeaway you need to take from the slide is just that it is possible to instantiate quantum computational pseudorandomness efficiently, under standard cryptographic assumptions. Okay, but now let's get back to our original question. So our original question was, are these CFT states a pseudorandom ensemble? Well, if so, that would imply their complexity is difficult to estimate. But the difficulty is that with these states, it's not clear that these states are capable of universal quantum computing, and therefore it's not clear that you could use this prior construction, right? So this means that it's kind of very not obvious that these states form a pseudorandom state ensemble, because we don't know how to connect the pseudorandomness of these states to kind of standard cryptographic assumptions like the existence of pseudorandom functions that were used by prior works. So in order to do this, we're going to use something differently. We're going to use a different pseudorandomness construction. In particular, we're going to use a construction that's inspired by block ciphers, such as the AES and the DES crypto system. And I'm going to skip this background on block ciphers first. I'll just kind of cut to the chase to get to our pseudorandomness construction, since we're out of time. So the basic idea with our construction is the following. So, okay, so as Raphael pointed out at the beginning of the talk, even though this unitary U is scrambling, the state that you apply by just applying U many times to the initial state, this state is not pseudorandom. Why is that? That's, as Raphael pointed out, you could just run the time evolution backwards and project onto the thermal field double state, and from that you would learn the amount of time that you evolved just by trying some handful of different times. Okay, but the basic idea of our construction is to do something different. The basic idea is that we're going to take these shocks and the basic idea is to apply these shocks to the system, but not reveal the pattern of shocks to someone else. And the basic idea is that these shocks can help obscure the length of an evolution to someone who didn't know what pattern of shocks that you applied. So these shocks will play the same role of a secret key in cryptographic construction. So let me say that a little more formally. So in particular, let's consider the following ensemble of states where you alternatively apply U, and then between each application of U, you apply a random 1-qubit poly operator. So your secret key K is now the identity of which poly operator you applied at each time. So for instance, you'll evolve by U, then say apply a poly X to the first qubit, then apply by U, then you might apply a poly Y to the next qubit, etc. And the basic idea is that these insertions of these shocks create branching points in the potential evolution of the system. So what do I mean by that? Well, if this unitary U were typical, say if it were a Haar random U, then then basically these states, this construction, each choice of a random poly operator I, X, Y, or Z, defines some branching in some tree. So what is this tree on the left-hand side? It's basically say, okay, you start with your initial tree, then you say either apply, one operator, you either apply identity or X or Y or Z to that state, that would fork your tree in 4 different ways, et cetera, et cetera. So, after L operator insertions, there are 4 to the L different states that you could end up with after this evolution. And the basic intuition is that if you were typical or Haar random, then every single state in this exponentially large tree would be nearly orthogonal to every other one and essentially random. So the basic claim of our pseudorandomness construction is that given some unknown state, say in this tree, it's very hard to tell if you generated the state through this process, say where that is to say, if you created the state, with some fixed but unknown shock pattern, or if the state was not in the tree at all. And the way that we argue for this is we give some sort of security proof for this statement in a kind of simplified black box model. So we say something like this, like suppose that our scrambling evolution were a random unitary, but you could only access this unitary in a black box manner. That's to say, the only thing you could do is time evolve your CFT forwards or backwards. Those are kind of, and say apply polytime computation in between. What we're able to show is that, kind of in this simplified model, the number of queries that you would need to U and U inverse to distinguish one of these random states from a hard random state scales exponentially in the number of operator insertions L. And so, this proof, so we kind of sketch an outline of this proof, and we conjecture that the security would still hold even in a white box model. That is to say, even in a model in which you knew the Hamiltonian, that is to say, U is the scrambling evolution of the CFT. But this is not something that we prove. Rather, we're conjecturing here that this Hamiltonian is sufficiently scrambling that that this pseudo-randomness construction makes sense. So, right, the intuition here is that once you apply one of these local operator insertions and then evolve the CFT for a scrambling time, that scrambling time evolution kind of just diffuses this perturbation you made to the system throughout the entire CFT in some very highly non-local way. And it's very difficult to then recover what operator you applied if you kind of iterate this many times.
So sorry,
Yeah.
so Adam, I have a question. So why is this thing still is a conjecture? Is that because it is hard to find an explicit construction of your oracles?
Sure. So there are two reasons. There are two reasons this is a conjecture. The main one is that you actually couldn't prove this statement unconditionally unless you prove something kind of similar to P not equal to NP. So pseudorandomness is something that only exists under cryptographic assumptions, and cryptography is only possible essentially if P is not equal to NP. So, so basically this is not something that would ever be within kind of even the range of complexity theory to ever hope to prove something like this unconditionally. Yeah, so and the second one is that, I don't know of kind of an explicit description of the CFT Hamiltonian in some kind of qubit model to work with to kind of even approach this question as to whether or not, it's scrambling enough for this to be a reasonable conjecture. But so that's kind of just that we're sticking our necks out there and we're just saying, look, if the CFT evolution is as scrambling as people think it is, then this evolution does look pseudo-random.
So can you just take your CFT to be a local Hamiltonian with some couplings, and you turn this couplings to the critical point, and then you have a CFT there? Yeah.
So this actually you could see this as some sort of, we're creating some sort of recipe or a candidate for creating a quantum pseudo-random state construction using scrambling dynamics of Hamiltonians. So yeah, you could view that as kind of yeah, that's one way of viewing our result basically.
Okay, thank you.
Good. Yeah, thanks. Great. So yeah, so that's kind of our security proof. And it turns out that the reason that the security of this statement is reasonable to conjecture from a computer science perspective is that it actually looks very similar to the methods of encryption called block ciphers, which are used to encrypt the internet. So let me explain that a little bit. So I claim that the following is a kind of very direct classical analog of this quantum pseudo-randomness construction. So what's the classical analog? Let's say that you fix some permutation sigma over n-bit strings. So this is an element of S2 to the n. It's some object that permutes n-bit strings. And let's say that sigma is a permutation that's very highly scrambling. So it kind of takes strings and it mixes them up a huge amount. So let's say that you have some bit string B and 0, 1 to the L. And let's consider defining some ensemble of 2 to the L states Y sub B, where the way that you create this string is you start with 0 to the N. You applied this known and very highly scrambling permutation sigma. Then, based on the first bit of B, you either flip the first bit of the string or not. Then you apply sigma again. Then you flip the first bit of the string according to the second bit of the key B, et cetera, and you repeat this L times. So the question, a natural question is, if you had a string Y, how hard would it be for you to tell if your string was YB for a randomly chosen bit string B, or if it was uniformly and independently random? That is to say, if it had nothing to do with this permutation sigma at all. It turns out that you can rigorously prove that if you only had black box access to sigma and sigma inverse, then you would need exponentially many queries to this black box in order to determine if YB came from this process or was random. And the reason this is true is the same reason that our kind of pseudo-randomness conjecture is reasonable. The basic intuition is that if you have a permutation that's very scrambling, then whether or not you flipped the first bit, after say the first round, kind of just scrambles that information very non-locally in kind of all the bits of the output. So, say after the first application of flipping the first bit of the string or not, kind of that just maps you to one of two possible random strings that are essentially independently random from one another. And therefore, after doing this L times, it basically means that YB is essentially a uniformly random string from some set of size 2 to the L. And the argument is basically there's no way of breaking that construction other than brute forcing it. So it turns out that this is actually very similar to classical block ciphers such as the AES crypto system. The only difference between these two is basically that in classical block ciphers, you tend to apply the whole secret key at each round rather than just dribbling it in one bit at a time. Unfortunately, I'm out of time, so I'm not going to go into the details of this. But you can see our result is kind of proposing this kind of fully quantum block cipher. Okay, so I'm going to kind of summarize our pseudo-randomness results. So in short, what we saw here is that the states in the CFT are plausibly pseudo-random. And what made this assumption reasonable, or this conjecture plausible, is that the scrambling nature of the CFT evolution is what makes our white box security conjecture plausible, because it makes it look a lot like a classical block cipher. And this immediately implies that estimating the length of time evolution of a conformal field theory state is something that should be exponentially difficult, even with a quantum computer. And the proof of this is very straightforward. You just say, well, just instantiate our pseudo-randomness construction with two different polynomial lengths of time evolution. Since each one is indistinguishable from Haar random states, that immediately implies they're indistinguishable from one another as well. And this implies, as a corollary, that any quantity that grows linearly with time is something that's hard to estimate. Okay, so, and then I'm going to skip through our volume results, but they're kind of the same statements that I was making earlier in the talk, which is that we gave this argument that with post-processing, one is able to compute wormhole volume, assuming the extended Church-Turing thesis. So I'm just going to wrap up with maybe some philosophical comments on what this result might mean for the AdS CFT correspondence. So I think that there are kind of two possible ways of viewing our statement that either the dictionary has to be exponentially complex, or the quantum extended Church-Turing thesis has to be false in wormhole interiors. So the first way of viewing it, which is somewhat described in a recent paper of Susskind, is, one might view that the complexity of the dictionary is a bug, but maybe it's something that's okay and possibly something that was even expected to occur behind black hole horizons. So in particular, in this work of Susskind in 2020, he made this conjecture, which he called the computational cosmic censorship conjecture, which is he conjectured that all violations of the quantum extended Church-Turing thesis, or exponentially complex dictionaries, are something that has to be shielded by horizons. So in other words, he conjectured that AdS CFT can be computationally efficient for wormhole exteriors, but any sort of area in AdS CFT where it becomes computationally difficult to perform the construction has to lie behind the horizon. And you can see this as kind of the complexity theory version of the cosmic censorship conjecture of Penrose, which is this conjecture that all singularities in GR have to be shielded by horizons. You can see this as a complexity version of that statement. There's another way of viewing this result in the context of AdS CFT, which is actually maybe not as diametrically opposing it as I'm painting it, but it's this idea that at least I first saw in the paper of Kim, Preskill, and Tang, which is that maybe the complexity of this dictionary is something that's a feature of the theory rather than the bug that we need to be burying behind horizons. So it could be that the fact that this dictionary between the exterior and the interior is exponentially complex is a way of providing some sort of computational protection of causality. So in particular, maybe the high complexity of this dictionary prevents someone from, being able to modify the CFT, something that's living at the boundary of the theory, and non-locally affect things that are occurring, say, in the wormhole interior, which are space-like separated. Kim, Preskill, and Tang actually talked about this in the context of one-sided black holes and the firewalls, but I think there could be an interesting way of maybe combining their perspective with AdS CFT and two-sided black holes instead of the one-sided black holes that they were originally writing about. But this perspective definitely syncs with this AdS CFT picture as well. And then finally, there's this nice question of what the quantum extended Church-Turing thesis could even look like for quantum gravity. Again, in our results, we use this quantum extended Church-Turing thesis as a black box. We just said, well, there should be some way of simulating the experiences of observers on the wormhole interior efficiently, but formalizing that would probably require answering a number of very interesting physics questions, like how does this AdS state actually encode the geometry of the bulk, and what are kind of relativistic considerations with rigorously defining what one means for efficient computation. But I think this kind of gives rise to a number of very interesting questions. All right, and with that, I'm going to wrap up and take any further questions. Thanks for your patience and letting me go over time, but I've really enjoyed the discussions along the way. Thanks so much.
Can I follow up on, I'm really intrigued by what you said in response to my earlier question,
Sure.
where I said, okay, I can live with the fact that the dictionary is very complicated.
Yeah.
And you said, but somehow it matters that it gets complicated already after a short time, after a polynomial time. Again, my naive reaction would have been, given the kind of states you're producing, I would not find it in the slightest bit surprising that if you handed me one of those states and challenged me to find the bulk dual, I would not expect it to be any easier than just directly computing in the CFT how complex that state is. I don't know why I should have expected that, and I think I might be missing something there.
Well, no, I think that the expectations for this, so I think that there was some intuition before that interior reconstruction was difficult. And if you already believed that, which it sounds like maybe you did, then I think our result is you could see it as a formalization of what's the obstacle to computing, what's happening within these wormhole interiors. So I think that prior there was already intuition that there should be, that this looks like a really thorny problem. But, but I think this is a way of putting your finger on, like, why is it difficult? The reason it's difficult is that you can instantiate block ciphers in the quantum theory, and that therefore cryptography is actually the reason, you could view it as the reason that this interior reconstruction is hard.
Thank you.
Yeah, no, it's a great question.
Adam, I wanted to ask a little bit about the necessity of horizons in the Susskind proposal.
Sure.
So in particular, like I think that your argument works whenever you have a two-sided wormhole.
Mm-hmm.
And so one situation where you can relate two-sided wormholes to geometries that have no horizons is in 3D gravity.
Mm-hmm.
So in particular in 3D gravity, if I identify geodesics and then kind of fold up the thing, I can construct two-sided wormholes out of just vacuum AdS 3.
Okay.
And so this leads me to a bit of a confusion, because it seems like if I do my identification correctly, I can make different two-sided wormhole geometries for which you would have said that the length of the wormhole maybe is something that is obscured. It is something that's highly complex, but the censorship thing maybe prevents it from doing so. But I could have just as easily not done the identification and acted on the parent Hilbert space, if you will, like the original CFT, without doing the identification. And in that situation, it seems like then there's no horizon to protect you in the way that Lenny is conjecturing.
Oh, interesting. Yeah,
so
yeah.
Then,
I don't think I'm familiar enough with the setting of 3D gravity for this, but with so you're saying that you think this contradicts Lenny's conjecture that this only occurs with horizons?
Well, I'm wondering if it has to do with if you're only allowed to act on like one side of the wormhole or both sides of the wormhole at the same time. Because if I'm acting on the entire parent CFT, then in some sense I'm acting on both sides of the wormhole. If I think about the identification, because the one copy of the CFT generates both CFTs in the new wormhole geometry. But nevertheless, it seems like if the statement is that high complexity things only arise when there's horizons, then it seems like I can learn the same information in two different ways. One way where there is a horizon, and one way there seemingly is not a horizon.
Well, I think the only way we were able to make this argument work, or why it had some interesting consequence, is that we knew there should be some information you could unlock from the interior, namely wormhole volume, that was this dual to complexity, right? So the statement that complexity itself is exponentially hard to feel, or amount of time is exponentially hard to feel, I think it's something that only becomes interesting when it's dual to a quantity that's feelable. And then that's what then means there has to be some high complexity thing kind of going on in the theory.
Yeah, I guess what I'm asking
in that setting, what would be the thing that's easy to feel that would be the dual to complexity that makes this a?
It would still be the wormhole length, right? If in 3D gravity I can use orbifold identifications to construct wormholes of arbitrary length that look the same from the perspective of the boundary.
Is it possible that the time evolution is different? If time evolution is different, after throwing in a little bit of light thing, whether it's scrambled or not, depends on Hamiltonian.
I don't think it can be, as long as the wormhole geometry that you generate is locally AdS 3, right? And I think it will.
The same Hamiltonian.
Yeah, it should be. I mean, this is why this conjecture was so striking to me, because it seems like this is a very easy way to falsify it. So I must be missing something, or like I just didn't think of this, which I doubt.
Yeah, is Lenny on the call to answer this? So
let me check.
Yeah, no. I don't see him on. Okay, great. Yeah, no, that's a great question to ask Lenny. So, good. Yeah, and any further questions?
Adam, actually, yeah, I have a question.
Sure.
So I guess in the context of AdS CFT, there's been a lot of discussion of quantum error correction in kind of thinking about recovering, states between both sides of the duality. And I guess the way that you're presenting it, it's basically a crypto problem. And I'm curious if like the connections between cryptography and like error correction are already like well known.
You could, that sounds like, yeah, I'm not sure off the top of my head, but I think in this context, what it might be saying is that even though the CFT could be in some sense some error correcting code of the bulk, yeah, encoding of the bulk. Maybe the encoding decoding operations are not in BQP, like are not efficiently.
I see. Okay.
Because, well, one could certainly create quantum error correcting codes that are not efficient to instantiate, like random codes, right? Also, those are actually pretty good quantum error correcting codes. So it could be that AdS CFT that error correction could look something like that.
Yeah. Okay.
Yeah.
Cool.
So Adam, I have to hear from your brief comment about some other related works. So aside from Nani's work and also John Prisco's work with his collaborators, so there is at least, as far as I know, 2 other related works. One is by Andrew, a postdoc in Caltech with his collaborator, I forget the name, and they prove that for estimating entropy, is the difference between entropies is as hard as learning with error. So there is another so related paper that is by John Soros and Jeffrey Pennington and Alex May. So they discuss the context of holographic scattering as a cryptography problem. So, and they say the holography seems to provide something that is novel for than the current cryptography, quantum cryptography theorems. So I wish to hear from, I'm not sure if you are familiar with those work, but especially the second one, it seems that it is telling you that there are something novel happens even for the AdS, pure AdS without a black hole inside. So which is kind of different from what Nani is saying in his paper, and he's saying that everything that is complete that looks fancy are requiring something like a black hole. So I'm happy to hear from your comment about those works.
Yeah, I think this is kind of related to the question I was asking, that you don't need horizons.
Yeah, I don't know about Lenny's paper. I think in terms of the paper of, this is the one of the first one you mentioned. That's of Andrew Georgiou, is that right? And
yes.
So I think I don't remember. I don't remember exactly what their construction looked like. So I think maybe what might differentiate our constructions is that in our construction we very carefully tried to make this problem from the dynamics of the CFT that was already allowed. Like, you were just allowed to evolve for scrambling time and then perturb, evolve for scrambling time and perturb. If you give yourself more universal forms of quantum computing, then that definitely opens a whole host of new cryptographic things that you could potentially instantiate. Like learning with errors things, or pseudo-random functions like in the Berkersky and Schmule and G-Leo Song constructions. So yeah, so I think this is maybe just the beginning of kind of exploring what sorts of cryptographic things could be there. But that's an interesting question as to whether or not maybe your second question was, are there some interesting new things we can learn in cryptography from these AdS CFT ideas? Yeah, I think that's a great idea. So that's a great question. And one thing is that this flip or not block cipher, where you kind of perform a normal block cipher, but just apply one bit at a time of the key instead of kind of applying the whole key all at once. To my knowledge, that's not something that was previously in the literature, and from some discussions I've had with Dan Bonnet and others about like crypto experts, that it's not known in the literature. So it could be that something like that could emerge. But I don't know so far.
I think Nani's wormhole conjecture is already an example. I mean, he has the intuition and wormhole side, and people figure out more rigorously in the statement of quantum information theory.
Yeah, no, that'd be very interesting. So, yeah. Great. Well, yeah. So if there are no more questions, then I'm more than happy to take follow-up questions by email and things like this. If anyone's interested in discussing that, just let me know.
Yeah, thank you, Adam, and let's thank Adam again for the seminar.
Thanks.